except mine. Can't trust other people's pens. Alright. So, we had one section left in chapter 2. And I already said a little bit about it, but there's more to it. So one thing about 2.8 is not talking about just a, or 3, or -7, but actually finding the derivative everywhere. So let's start with a problem you saw on the test, but let's adjust it a little bit. Let's see, let's do this. Remember we've done this already. So some of you guys had like square root of x minus 1 on there, square root of 3x on there, something like that. Or one of your problems. And you're like, I can't remember, that's like yesterday. So in section 2.7, they restrict the way they look at it as finding the slope at a certain point, or even a. But we can do the same process and just leave x in there, and then we can plug whatever point we're interested in the future. And this is how we start to develop shortcuts. So let me do this. To lead into today's, let me go ahead and change this. I'm just going to change that. Maybe it's a little more interesting. So what's the more accepted method? I mean, either one of them is valid, but this one is more accepted because it's more general, is this guy. So how would I set this up?
X plus H.
F of? Yeah, F. So let's put the actual function. X plus H cubed, I'm with you.
Minus X cubed.
Minus X cubed, I like it. Good, I like it. And of course, you can see that it is currently in indeterminate form. Anytime you set up a derivative limit, it will be indeterminate. Today we're actually going to use this to figure out the derivative of sine also. I think that was a bonus question on the test, if I remember correctly. So you guys can see if you got that right if you tried it out. Alright, so what can I do here? And I like somebody's approach. I didn't say this, but the top is in a certain form that you can use to your advantage. Or not. You could FOIL this out a few times, right? Or, what FOIL sort of represents. Or there's another way to do it. What do I have to do something? What is it that tells me I have to do something? Algebraic to this. I have to do something algebraic.
You have to solve the problem because you can't have the h at the bottom all by itself.
You could if the top was a constant, but this is 0 over 0 at 0, right? So that's why I got to do something algebraic. So I could distribute this, FOIL this out, blah, blah, blah. But let's try something different. So you guys, because you need to start looking at things and not be so scared of factoring, for example. The top is in a certain factoring form. The top is a difference of cubes. And of course, that's one of the least liked factoring. Poor little dude. It's not nice. It's not. So watch. Just remind you guys. Watch how silly this is. Little dude, big dude.
Oh yes. Okay.
Little dude, big dude. So one of each in the little dude. Why? Because it's the little dude.
And then
I need 3 overall, so how many in the big dude?
A squared.
Yeah, 2 in the big dude. So overall I do get 3, but then I get this cross term shit. And I remember what was the guy's name in Pulp Fiction, the cleaner, when they shot the kid's head in the back of the car. Never seen it, I'm sorry. Just gave away something big. The kid lives for a little while, and then if you haven't seen Pulp Fiction, I don't understand. But this guy's a cleanup guy, because I get my a cubed, but I also get minus ba squared, right? You guys with me? This is how I'm familiar. So this middle term, so I get minus ba squared, and you put it in alphabetical order if you like alphabetical order, and I get plus ab squared, those cross terms. So if I make the middle term the opposite sign, which makes sense because it's supposed to cancel the shit out that I don't want, ab. So now what do I get? What's a times ab?
A squared.
A squared b kills that. What's b? Negative b times ab? Minus ab squared kills that. And I'm just left with a cubed minus b cubed. So difference of cubes, sum of cubes, same thing as one of each in the little dude, 2 of each in the big dude, product in the middle. It's not hard. Yes?
But that has to be a plus b squared at the end.
Yeah, sorry. Yeah. So there's a little thing, and I kind of hate mnemonic devices, but screw it. Same, opposite, always positive. Soap. Right? And students just eat it up. But to me, it's just silly. That's always the same sign. Why is that a different sign? It's the cleanup dude. He's got to kill the shit, so of course it's got to be the opposite sign. And that's already minus, so why would that be anything other? Whatever sign this is, it already sets up what that is. So it's got to be positive, so it doesn't screw with that sign. Or soap. Why not? Right? I know students don't understand me sometimes, but I don't like too many mnemonic devices, because then you're getting further away from the idea. And the ideas are what's most important in math. But sure, what the hell? So how do I factor this dude? Yeah, the little dude's going to have x plus h minus h. That looks better already. Minus x, sorry. That looks even better, Jeff. There it is. So one of these minus one of these. And the big ass dude's going to have two of these. Plus x times x plus h. Plus x squared. Kick ass. And by the way, you do not have to do this. I just want to show you a different way. You could just do this cube that bad boy. That's what the hell. That's fine. So this is just going to be h, and that's going to. And see, now I can just plug 0 in because I killed my problem.
Dead.
0 over 0, no more, because I killed the part that was making him 0, right? So what do I get when I plug a 0 in? Of course, I lost. Oh, I'm sorry?
2x squared.
Yeah, you'll get x squared plus x squared plus x squared, 3x squared. So to use the right symbol here, what symbol would I use to designate this?
F
prime. So that prime designates the derivative. Another way to say this is this notation here. So this is new notation. I don't think I've shown you this before. Yes, dx f of x. So that's the derivative of that function. So those really do kind of mean the same thing. Yes.
What's the difference when people put dy over dx or just d over dx?
Well, what's f of x? Y.
Okay.
So this is just dy dx then, if you just replace that with y. Is that cool? I like it. I like it. And the reason this is actually a little better, this notation is better, and of course students normally know this notation, because this, do I always have the variable x? And do I always have only one variable? So this is very specific. It tells me what I'm taking the derivative with respect to. And in this case, it's kind of silly. Of course, I would use this notation because there's only one freaking variable in there, so it's got to be with respect to that value.
Was that Newton who did a d over dx, or?
Oh crap! I always forget. Newton did. I have it on my own. Why do I say the left side? Yeah, it's Leibniz and Lagrange actually. I think this is. Why do I not remember? Newton did this, which physicists use that notation. So that would mean the same thing as dx dt with respect to time, because in physics you have a lot of rates, right? The derivative with respect to time. So we use a little dot for that, and a double dot for acceleration, for example. The second derivative. I like it. Cool. What was my point with that? Oh yeah, so now if I wanted to know the equation of the tangent line for f of x equal to x cubed at 2, 8. What two things do you need for the equation of a line? Slope. How do I get the slope?
From the f prime.
Yeah, I've got the slope everywhere. The slope everywhere is defined by this. So specifically, the slope at what? 2 is going to be, 3 times 2 squared, 12. Which makes sense. When you make a cube, it starts to rise really pretty quickly, right? And then the point, of course, is very nicely given to me, 2, 8. And then you just have to plug and chug into either equation of a line So just to be a little different, we can use y minus y1 equals m times x minus x1. And then solve that for y and make it look nicer. So that'll be y equals 12x minus 16.
Yes.
Yay! Jeff can add. So if you plotted this and that on the same axes, that would touch this once at that point, right at that point. Right? It would be tangent right at that point. So right at the point, it would be around. And it makes sense. It's got a positive slope and it's got a negative y-intercept. All right? Okay, good. Nowhere near good enough for your homework to turn into me. Right? And I still do get some of that.
Numbers, counties.
Yes, something. Some landmarks there for me. Okay. All right, so good. That was a little stroll down memory lane. But now look what happened there. This is interesting. And I sort of, it's funny that I did this. I wanted to do this, but I also wanted to do it the other way. But if you did multiply this out, let me see. Let's do this real quick. Stay with me. Because see, this is not enough for a pattern, but what does it look like happened, and some of you guys know this rule, what does it look like happened from the function to its derivative?
Move the 3 over.
The 3 came down,
Subtract 1.
and the power went down by 1. Right? And we've done some parabolas in the past, and it seems to be the same kind of thing. The 2 comes down. I like it. And just really quickly, I've got the more general idea on this handout, but just very quickly up here. If you did multiply this out, wouldn't it be x cubed? And this is where Pascal's triangle is just so kick-ass.
Plus 3.
Yeah, it's 1, 3, 3, 1 for that row on Pascal's triangle. Or just multiply, multiply, multiply. Either way. So it's x cubed. So it's all x's. Then it's 3, 1 less x, 1 more h. Then it's 3, 1 less x, 1 more h. And then it's all h's. So that's this. That's beautiful. The more you know, the less you got to do. And so these, you see what happened? Look what happens. The x cubes die. So of course, if this is the 4th power, wouldn't essentially the same thing happen? Stay with me now. It would be x4 here, and then this is minus x4, so they would go away. But then what would the next term be? It would be 4 x cubed h and so forth, right?
Yeah.
So what's about to happen? Those went away. So what can I do with my h's now? So the only thing without an h is that guy. So when I let h go to 0, 3x squared. Now I'm doing this not very neatly. You never do anything neatly, Jeff, that's right. But that's even messy for me, because we already did the freaking work. But I just want to point out, does it make sense? If that was a 5th power, essentially the same thing would happen, except it'd be 5. So that's why it looks like that comes down, because that's, the 5th power has a 5 here, the 6th power has a 6 there. It's awesome. Yes?
Shouldn't you always just look at the second term after you fold it out, and that will be your answer, I guess, your slope of the tangent line? I mean, the equation of the slope of the tangent line.
So look at, I'm sorry?
Okay, I'm saying, so you always look at the second term after you fold it out. So in this case, it'll be the 3x squared h, and then you just look at the 3x squared, and now is that always going to be your...
Well, don't make too many generalizations. In this case, it's because if I let h go to 0, every other term has an h in it, so that's the only one that's left. Don't try to generalize that too much, because if the function doesn't look like that, it's not going to be the same kind of thing. But the generalization that we can make, let me see if you guys are ready for this. I know a few of you already know the rule. But for those of you who don't know the rule, can I generalize this for x to the n? If I have f of x equals x to the n, what would f prime of x be? Alright. That's the rule. And what do you think I should call this rule? That's insane, because it's all about x to the power. So we call this the power rule, because math people are very creative.
What are we going to call this thing?
It's got powers.
I call it cup of dirt.
Brian, yes.
Just move on.
No, tell me about it, Brian. Alright. So that was actually, I kind of went off, bad calculus pun, I kind of went off on tangent there. I went back to 2/8. So here's what 2/8's all about. This is, normally students love this. I just want to let you know what I mean when I say that. But please, this does take some getting used to. So I'm going to do one of these with you. I'm going to make you do another set of these. What are they?
Today we're going to do math.
It's like when I was younger. Mom, what are we having for supper? Food. Oh, for a change? Smack. That was basically. Alright. Sure, this is going to be interesting. So I'm just going to do one of these as an example, and then I've got another couple for you to do on your own. So what we're about to do is we're given a graph of a function. We're going to try to graph its slope. So the weird thing for us that we got to get used to is the slope of anything that's not always a straight line going in the same direction is going to be some kind of a curve of its own. So some of you guys know all too well where I'm going with this. You can almost see that.
The absolute value of x.
Yes, cool. I like it. So I want to start with something easy. And believe it or not, this is easy because it's really just two straight lines. The reason this is easy then is the slope never changes until it gets to what number? 0. And then the slope abruptly changes. So I'm going to graph the derivative, which means I'm going to put points by drawing a line that represent what the slope is at that point. And this is what's really hard to keep in your head. And trust me, it's hard for people that even know this shit really well. You got to keep reminding yourself what you're doing. Otherwise, you just start to follow the curve and like, what the? So what am I talking about? Can somebody tell me what the slope for every x back here below 0? What's the slope? -1. Right? Not what the equation is, but the slope is going to be down 1 over 1. So it's -1. So how would I plot the slope then up to 0? At this point, what's the slope? -1. So I'm going to put a point right there. Do you guys see that? Do you guys see what I'm saying?
Yeah.
So what's the slope at this point? So I can just make a line that represents. Well, at 0, this is interesting. Well, let's do this. Let me just leave that a little not done yet. Right. Whoa.
What is the slope at 0?
Oh, let's find out.
Absolute value of 0.
But that's not the question. The slope of the absolute value function at 0. No, it's not. So you ready? What is it up here?
1.
Every point, at this point it's 1. At this point it's 1. So it's going to look like this. So this change, it's a gradual change through 0. No, it's a very abrupt change. So at 0, it doesn't round off. If it was like the parabola, then it would be 0 there. But I really want this to make sense. Let me make an upside down parabola. Let me make an upside down. So this makes total sense. So here's so I could balance a tangent line on that parabola, right? I can balance it there. All right. So now let me just turn the absolute value upside down. And that makes sense because if I have a particle moving like this, right at this point it wants to go that way. But then gravity pulls it back down or whatever. Right? So if I have a particle right at this point, it wants to keep going up. Or if I have a particle right at this point, it was coming from something down. So this is interesting. This is almost like the idea of continuity. So is the derivative continuous through the point 0? No, because it abruptly changes. So I can't draw a tangent line that makes any sense. That would just go, no, it's no good.
You have a hole.
Exactly, you have two holes. You have a hole there and a hole there. So it is what kind of discontinuity?
Jump.
Jump. And it's even like a little worse. It's not defined anywhere in 0. So the slope, the derivative of the absolute value of 0 is not defined. Cool. I like it. All right, let me stop there for a second. So the bigger idea here, that was just a weird thing about absolute value. The bigger idea here is everywhere I draw, when I'm drawing the derivative, I'm thinking I am representing the value of the slope at the x that I'm currently looking at. So let's do one that's a little more interesting. This is not very curvy. That was kind of boring. All right. Now, anybody happen to know what that roughly would be, or is negative x cubed? Kick ass, because it's got the reverse end behavior, right? And what should the derivative of negative x cubed using our
Negative 3x squared.
negative 3x squared? So when I draw this, I already kind of know it should look like what?
Upside down parabola.
Upside down parabola. So I know that going in, but don't just do one and go, don't do that either. I don't know what the hell is that. So when I draw derivatives of more interesting functions, functions that are curvy, functions that really change everywhere, where do you think the really smart thing to do to start? Where do I know the slope just for certain? I just know what the slope is. Don't have to do it. Yeah. Where is the slope 0? Roughly. Yeah, at 0, it's definitely 0. The slope is 0. 1 point something or other, right? You stop there. So those are my anchor points. I always start there if it's a curvy. If it's absolute value, there's nowhere the freaking thing is 0, really. So I don't start there. Let me stop there for a second. So I know my derivative graph that I'm going to draw has to go through those points. Now here's where here's where the disconnect is. People start to draw it, they're like, it's positive. No, what's the slope for x values below 0? What's the slope? Negative. In fact, the slope here is big ass negative, right?
Yeah.
And I'm not going to make you be very overly specific. You don't have to lay down transient lines over here and try to get the exact answer. I just know it's really big negative, and what's it doing? Like here, it's big negative, but it keeps getting what? Less negative, so I would accept bigger. Right? It's being less negative. So it starts off really big negative, so maybe, let me just do this once. Well, Jeff, it's your class. Do whatever the hell you want to. So the tangent line here is roughly like that. Is that cool? The tangent line right here roughly goes from that point to that point. Is that decent? So right here, this x value here, let me try to approximate what the slope is. So it goes down 1, 2, 3. Oh, that's not really 3. That's gross. That's too bad for us. So it goes down 2 point. What is this? Is this 2, 4, 6, 8? No. What are those points? Okay, 0.25. I just had like my 8. So this is like 2.75. No, Jeff, that's the opposite. This is like negative 1, 2.75. Is that cool? And this point is like negative 0.5, 0. So what's the slope between those 2 points? It would be 2.75 minus 0 over negative 1 minus negative 0.5. So what's that going to be? It's going to be 2.75 divided by negative 0.5?
Yeah. So
it's going to be like 5.5. Sorry? Yeah, I'm sorry. Negative. So then my official graph should be at negative 5.5. Should be way the hell down here somewhere. So at that x value, at this x value, the slope is roughly negative 5.5. So if I'm drawing the slope, I'd have to put the value here at negative 5.5. So all I know is it starts off really big negative, and then it comes up and is less and less and less negative, and then it goes to 0. So does that make sense? Everywhere, all the points that go through this green line, or to you guys just that line, what do they represent? They represent the slopes of this at each of those x values. So everywhere along that function back there, it's negative slope. But what's happening as they go around, as they approach the curve, as they approach the bottom of that, they're getting less and less and less negative. They're approaching 0 slope, aren't they? So what's my function doing? It's getting less and less negative as they get closer to 0, less and less and less negative. and then it goes through 0. Now what happens after that curve? What happens? The slope now gets more and more positive. Can you guys help me out? At that point it's 0, right? Somewhere in the middle here is a very interesting point. Those of you who have calc before, maybe just sit on it for a little bit. The slope is getting bigger, 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 right? But somewhere here, isn't the slope getting smaller, 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 so it's 0?
Yeah.
So right somewhere here, there's a point where the slope is the what? So right now it's 0 slope, right? Then it's getting bigger, and then up there it's getting smaller. So in the middle, somewhere where the slope is the biggest. Slope is the biggest. Does that make sense? So somewhere here, in fact, let me just come over here. So right here, the slope is positive, but it's not very big.
Right.
As I go around the corner, it gets bigger and bigger. But then up here, it starts to get smaller and smaller and smaller until it's 0. So in the middle here somewhere is what we'll eventually call the inflection point. This is where the slope itself, the change in the slope switches. Yeah, exactly. So right at that point in the middle, it's going to be where it's the highest value. That's beautiful, Jeff. Oh, too bad. Yummy, yummy, yummy. And then what happens after I move past this? What happens to the slope now? More and more and more negative. So did the results, as beautiful as that is, did it match what we knew should happen because it was a negative x cubed? The result should be a upside down parabola. And that's exactly what happened. But when students do this, you start fine, and then you start to follow the function. And no, there actually are some functions that are their own derivatives. So we'll hit that, and of course, if you've had calc before, you already know. So what I want you to do.
So that graph that you just drew in, that's the graph.
Yeah. So this is f of x. This is f prime of x. You guess, or a rough
So you
approximation.
just graph it by plotting your slope values.
Yeah, you do not have to do what I did up here. That's why I did it so quick and ugly. I don't want you to really do that, to be honest, because that was what chapter 2 is about. This is more of an idea where you plot down. It starts off really big negative, so start really big negative, and then it's less and less negative until it's 0. And you just keep following it. But you got to keep telling your brain, I'm plotting the slopes, right? I don't care what the function, if it's positive or negative. I just care what the slope is doing. So if I pick this whole function up, if I pick the actual f of x and moved it up or down, would my downward parabola, would it change at all?
No.
No, it wouldn't. It wouldn't care. All that this thing cares about is the shape of my graph. It has nothing to do with how high up or down my graph is. Because if I just picked this up and moved it down, the slope is still going to be 0 at the same place, isn't it? It's still going to be 0 slope at the same place. It's still going to be negative at the same places, positive at the same places. All right, good, good, good.
Is that because the derivative of a constant is 0?
Well, that's true. But there's no constants up here. Really.
No, but like when you said like if you move it up and down, you're moving.
Oh, okay, yes, okay, I'm with you. And of course, if you've ever gone far enough for the integration, it's the whole plus c thing.
Yeah.
Yes, okay, good. And all right, so let me give you your own. And unfortunately, well, it's not unfortunately, actually, it's actually better that there's no grid. Because I don't want you to freak out about precise values. So do what I just did for this, and then we'll do it together. So this is not a quiz. I'm not going to see these unless you show it to me. So be real free to mess up. This is the time to do it. Like that's exactly what I'm planning on doing. Determine my whole plan. What's that? Okay. Actually, once we're done with this, we're going to head out. I think we're already done both things I wanted to do once this is done. I don't think I've ever looked at the clock after, and it wasn't after 1. It's like, what the hell happens? There's a temporal problem.